This is lecture 16 in BBSP 610. We'll be discussing hypothesis tests for categorical data. Thus far, we've primarily discussed hypothesis tests for means and proportions, basically things with continuous data. Well, actually, in a certain sense, proportions are categorical data, but we won't worry about that for now. I don't want to confuse you too badly. But in general, if you're measuring a continuous number, then then you would be doing hypothesis tests on the mean. If you collect 100 people, measure how tall they are, that's in theory a continuous number. And you would take the average, calculate confidence intervals we've discussed previously. But if your data is counts, then you have categorical data and t-tests won't work. You have to use certain other methods. That, for example, say that you administer a drug and a placebo to the participants in a study, and they either report pain relief or no pain relief, a binary outcome. In this case, they fall into one of four categories: drug with pain, drug with pain relief, drug with no pain relief, placebo with pain relief, and placebo with no pain relief, and you just have a count of each one. Or maybe you have three categories of no pain relief, some pain relief, or complete pain relief. Or maybe you measure the accounts of certain phenotypes in a genotyping experiment and you want to know if it's consistent, or I shouldn't say phenotypes, you just measure the allele frequencies in a genotyping experiment. You want to know if they're consistent with Hardy-Weinberg equilibrium. All of these are examples of hypothesis tests on categorical data. The proportion tests that we discussed in the previous lecture are one example of hypothesis tests on categorical data. Today we'll discuss some other tests that can be used in more general situations. The most basic and far and away the most commonly used hypothesis test for categorical data is what's known as a chi-square test. That basically, say you have a random sample of n categorical observations and you want to test the null hypothesis that the proportions in a given category are equal to some value. This will probably make more sense with an example. Let's say that you're growing snapdragons in an agricultural experiment and they can have either red, pink, or white flowers. And let's suppose that we believe that this red coloring trait is a codominant trait, that is, that to get a red flower you need two red alleles, to get a pink flower you need one red and one pink, and to get a white flower you need two white alleles. So under a Mendelian genetics model, if you have a set of pink flowers and you self-pollinate them, you should get progeny that are red, pink, and white in the ratio 1 to 2 to 1. Or in other words, the probability of red should be 0.25, the probability of pink should be 0.5, and the probability of white should be 0.25. Say we do an experiment to test this hypothesis and we get 54 red flowers, 122 pink flowers, and 58 white flowers. We want to see, is our data consistent with this null hypothesis? So under this particular null hypothesis, well, the first step in testing this hypothesis is you have to calculate what the numbers of each type of plant you would expect to see if the null hypothesis is true. If the null hypothesis is true, we would expect to see 234 times 0.25, or about 58.5 pink plants, and 58.5 red plants, 117 pink plants, and 58.5 white plants. And we want to see, are our observed frequency close enough to these expected frequencies? If they are, then we'll fail to reject the null hypothesis, but if we see a big difference, then we'll reject the null hypothesis. You can test this hypothesis using a chi-square test the given and observed frequencies OI, then you calculate expected frequencies EI the way we did on the previous slide. If for each possible category you take observed minus expected and square it and divide it by expected, that will have a chi-square distribution with n minus 1 degrees of freedom. Note in passing, a chi-square distribution with 1 degrees of freedom is just the square of a normal distribution. If you take something that's a standard normal distribution and square it, you get a chi-square distribution with 1 degree of freedom. And if you add together 3 chi-squares with 1 degree of freedom, you get a chi-square random variable with 3 degrees of freedom. That's not something that you'll ever need to use in this class. I'm just mentioning that for your information. Any rate, to calculate this on the Snapdragon data, remember the observed values were 54, 122, and 58, so we take 54 minus 58.5 squared divided by 58.5, that is observed minus expected squared divided by expected, plus once again observed minus expected squared divided by expected. Take the sum across all three, and we can do this in R, and the command in R to get the appropriate p-value is called p chi-square. You can see there I type the code that you use to compute the chi-square statistic, then I say comma 2 because it has 2 degrees of freedom, and then I subtract that from 1 because I want the area above, or I want the area the top of the tail, not the bottom of the tail. And p chi-squared, p norm, whatever, always will give you the bottom of the distribution. So in general, in R, p chi-squared of x comma df will give you the probability that a chi-square distribution with df degrees of freedom is less than x. In practice, you always want the probability that it's greater than x. The chi-square statistic is greater than you would expect, so you'll want to do 1 minus p chi-squared. And an easier way to do this in R is with the chi-square.test command. With the chi-square.test command, I just give the observed counts and then the expected counts under the null distribution and end up with a p-value similar to what we got earlier. And in general, in R, if you say chi-square.test of x comma p, that will test the null hypothesis. The observed frequencies in x match the expected proportions in p. And you can use this chi-square.test command for other situations, as we'll see here in a few minutes. So let's go back to this clinical trial example that we considered in the previous lecture. Suppose that we're conducting a clinical trial for a new pain medication, and we want to see if the new drug provides better pain relief than a placebo. We discussed this in the previous lecture, but now we'll do this using a different approach, using the chi-square test. That, in this case, it's slightly different from the earlier example. The earlier example, we just had 3 categories and had probabilities about the categories. But here, we have kind of a 2-by-2 table. And the null hypothesis we want to test is that treatment and pain relief are independent of one another, that whether or not you have pain, whether or not you got the drug or the placebo has no association with whether or not you experienced pain relief. And using the fact that the rows and columns should be independent under the null hypothesis, we can calculate the expected cell counts similar to what we did in our previous homework assignment. That if treatment and pain relief are independent, then for both the treatment and placebo groups, 51.4% of the patients should experience pain relief. So among the treatment patients, we would expect that's just the total number of those who experienced pain. 127 is the total number that experienced pain relief in either group, and 247 is the total number of people in the study, so 51.4% experienced pain relief. So among the treatment patients, would expect to observe 125 times 0.514, that is 64.27 patients with pain relief and 60.73 patients with no pain relief. So in general, the formula for finding the expected count of a cell in this type of table is you take the row total times the column total divided by the overall total. That the total proportions, the total proportion of or the total number of people in the treatment group who experience pain relief should be 125 times 127 divided by 247, and once again the numbers apparently got cut off when I converted this table to Keynote, and I apologize for that. The PDF on Sakai should have all the numbers. And in general, when you do a chi-square test for a contingency table, it doesn't have to be a 2 by 2 table, it could be a 3 by 2 or 3 by 3 or whatever the case may be, is that given observed cell counts OI and corresponding expected cell counts EI, the statistic, if you take observed minus expected squared divided by expected and add all those together, that should have a chi-square distribution with r minus 1 times c minus 1 degrees of freedom, where r and c are the number of rows and columns in the table. Oh, for the clinical trial data, here the observed and expected cell counts are in the table below. We observed 75 people with pain relief in the treatment group. We expected to observe 64.3. And we expect to observe 60.7 who didn't get pain relief in the treatment group. In fact, there were only 50. So just eyeballing this, it looks like there's more people who got pain relief in the treatment group and less people who got pain relief in the placebo group than we would have expected due to chance. Let's formally test this using a statistical test. So you can compute this directly in R using the formula I gave on the previous slide. It's a pain, I don't really recommend it, but you can count the expected count for each cell and then take observed minus expected squared divided by expected plus observed minus expected squared divided by expected, add them all together. In this case there's 1 degree of freedom because there's 2 rows and 2 columns. 2 minus 1 times 2 minus 1 is 1. We get a p-value of about 0.006, so we reject the null hypothesis of no association between treatment group and pain relief. A simpler way to do this in R is to use the chi-square.test command. What I do is create what's known as a matrix in R. You can see I say clinical trial equals matrix with 2 rows and 2 columns. Then I fill in each row of the matrix 75, or each cell of the matrix 75, 50, 52, 70. If I type clin.trial in R, see I get the numbers in matrix format. Once you have those numbers in matrix format, I can say chi-square.test clin.trial, the name of the matrix, and it will give me the test statistic and p-value. You'll notice the p-value is slightly different than what we got when we calculated it by hand. If I repeat the command and say clin.trial and then add the parameter correct equals false, then I get a p-value that's identical to what we saw on the previous slide. So in general, if you say chi-square.test of x, that will test the null hypothesis that the rows and columns of x are independent of one another if x is a matrix. If you need to reproduce the results that you would get doing a chi-square test by hand, you can add the flag correct equals false. I don't know why you would ever need to do that unless you were in some other statistics class and they wouldn't let you use R and you wanted to check that you did it right by hand. I'm never going to ask you to do this by hand in this class. R is perfectly fine with me. And note about matrices in R, the command matrix, where you say nrow equals nr, ncol equals nc. That'll create a matrix object with nr rows and nc columns. To reference the ith row and jth column of a matrix in R, you can say x bracket I comma j. Then you can fill in either, and you can either extract the ith row and jth column or assign a certain value, or assign a certain cell a certain value. Another way you can do this if you want to save yourself some typing is just use the matrix command directly in chi-square.test, being sure to specify that there's 2 rows, and you can see that you get the same numbers that we got on the previous slide. And if you simply say x equals matrix nrow equals 2, ncol equals 2, that'll create an empty matrix where every element of x will be a missing value. On the other hand, if you say x equals matrix 1, 2, 3, 4 with 2 rows, it'll create a matrix containing the values 1, 2, 3, and 4. It'll do it by columns, so matrix X would have 1, 3 on the first row, 2, 4 on the second row, because it enters 1, 2 in the first column, then 3, 4 in the second column. And in order for chi-square test to give you valid results, the usual rule of thumb is that they're valid if all the expected cell counts are greater than 5. I found in practice usually the results are fine even if this condition is violated, but if that condition is satisfied, you should be fine. If it's not satisfied, R will give you a warning, and it might be a good idea to avoid using chi-square tests in those cases, but there's a couple alternatives that you can use to make sure that your results are valid even if the expected counts are low. So here's an example that I found from a book on a procedure called extracorporeal membrane oxygenation, or ECMO. It's a potentially life-saving procedure that's used to treat newborn babies who have respiratory failure. There was an experiment conducted in which 29 babies were treated with ECMO and 10 babies were treated with conventional therapy. So the results are in the table here, and we want to know, is the death rate lower for ECMO? Just eyeballing it, it looks like it's significantly better. We only got 1 death out of 29 with ECMO, whereas almost half the babies died using conventional therapy. We want to do a test to verify that. So the naive approach is to just plug this into chi-square.test in R. We can use the same notation that we used earlier, chi-square.test to matrix 46128, and we get a p-value of 0.015. Looks like there's evidence against the null hypothesis, but you can see it's giving us a warning message that the approximation may be incorrect. When that happens, there's a couple things that you can do to try to improve this situation. One is to add the option simulate.p.value equals true to chi-square.test, and this time you can see we get a smaller p-value, 0.008, and it doesn't give us a warning that the expected cell count is too small. So what did we do exactly when we added that parameter? Well, simulate.p.value tells R that rather than using normal distribution theory to find the cutoff values for chi-square.test, that it should do a simulated chi-square test. I won't go into the details of how it does that. But the basic idea is the R generates a bunch of random data under the assumption the null hypothesis is true, and then counts how many times this random data produces test statistics that are more extreme than what we got using the observed data. You don't need to worry about the details for this class. An alternative approach is to use what's known as Fisher's exact test, which has exactly the same syntax as chi-square.test, but rather than chi-square.test, it's Fisher.test. And you can see here it gives us a p-value that's very close to what the chi-square p-value gave us. This kind of illustrates what I said earlier, that even if your expected cell counts are less than 5, in my experience usually the results aren't too bad, but you can use these alternatives if you want to be safe. So Fisher.test performs what's known as Fisher's exact test. It calculates the exact distribution of the test statistic under the null hypothesis and then produces an exact p-value. The syntax is completely identical to chi-square.test. If you want Fisher.test, you just change chi-square.test to Fisher.test and you're done. So now we've described 3 different types of tests: regular chi-square test, chi-squared tests with simulated p-values, and Fisher's exact test. And they all can be used for the same types of data, so this raises the question of when should you use each one. And for this class, I'm not going to be super picky about this, but if you're wondering about this in general, here's some guidelines that you can use. The regular chi-square tests are far and away the most commonly used tests. They're simple and easy to understand, and in almost all cases they'll produce good results. The one drawback is if your expected counts are small, there are situations where the results are unreliable. It doesn't happen much in practice, but it can happen. The advantage to simulated chi-square tests are that it doesn't matter how small the expected cell counts are, you will get valid p-values no matter what. The disadvantage to these simulated chi-square tests is that they're hard to understand and hard to explain, and you may have journal editors or reviewers scratching their heads if you use them, which goes to the second point, that they're not used very often, so readers of your journal articles won't necessarily have seen them before. Reviewers might freak out and wonder why on earth you're doing this strange test that nobody uses. The p-values and confidence intervals are only approximate. If you do a sufficient number of simulations, the results shouldn't vary much, but if you want completely reproducible research, the p-value can vary slightly if you run this multiple times, and as a result they're not completely reproducible. Particularly for large matrices, they can be slow to compute, although generally speaking they're not that slow. I mean, honestly, in my opinion, the simulated chi-square test is underused. It has a lot of nice properties. The main reason I don't push it harder is just, like I said, pure inertia, that people don't use it that much, and so it raises eyebrows when you do use it. Fisher's exact test also produces exact p-values and will produce them even if your data is messy, if your expected counts are small. The drawbacks is that they're not commonly used, although they're used more frequently than the ones with simulated p-values. In particular, you will see Fisher's exact test in genetic studies and so forth. There's something of a black box in that the formula to compute it is very complicated. I don't even think there's a closed form expression for it for anything larger than a 2x2 table. And for bigger tables, it can be expensive computationally, and it can also be numerically unstable, that sometimes R will blow up saying that it ran out of memory if you try to use these, or sometimes it'll just give you weird results. So what should you use in practice? Honestly, if you just use the chi-square test for everything, you probably won't go too far wrong. You may want to use one of the other tests as a sanity check if R gives you a warning from chi-square.test, just to make sure the p-value doesn't change that much. Most of the time it won't, and if it doesn't, then you're fine. But if you're writing a grant proposal or something like that, and you expect to have small counts, and you don't want to deal with flack from reviewers saying that your approach is invalid because your counts are too small, you can say we'll use Fisher's exact test. So the things to remember for today's lecture are that we can test hypotheses about categorical data using chi-square tests. You can either test hypotheses about a single set of proportions or whether several categorical variables are independent of one another. And if the expected counts in a chi-square test are small, you may need to consider some alternative approaches. The R commands to remember today would be chi-square.test. If you give it a list of counts and a list of probabilities, it'll test the null hypothesis that the counts have the proportions specified in the probabilities. If you just give it a matrix, then it'll test the null hypothesis that the rows and columns are independent. If you add simulate.p.value equals true, then it'll calculate a simulated null hypothesis which can produce better results when the expected counts are small. Fisher.test will do Fisher's exact test, has exactly the same syntax as chi-square.test. And if you say matrix fex nrow equals nr ncol equals nc, that'll create a matrix containing the data x with the specified number of rows and columns.